Okay. Okay. Assalamu alaikum, everybody. This is, according to my counts, lecture 27, and it's the third part of talking about the complexity class NP hard in NP complete, and we are continuing our theme of reducing problems from a known NP hard problem to a problem of unknown complexity, so that it could also be included in the NP hard or NP complete set of problems. Before I formally start with the problems of today, couple of things. One, who is doing lecture notes today? Because we should do that, I think. I think we decided it last time. Can you guys just unmute your mic and say that you're here? Okay, I guess you're not here. So, how about the people who said they are going to do it on Tuesday? Are you available? Can you do it today? For the next Tuesday? Hello? Who said they wanted to do it next Tuesday? Okay. I can't hear anyone. Is it Afrazia? Can you hear me?
Yes, sir.
Okay.
Can you
Are
hear
you
me also?
can you do the lecture notes today?
Yes, I will.
Okay, cool. Afrazia and Kutsi are doing the lecture notes today. Awesome. And who did the lecture notes last Tuesday in our last class? Okay. Um. Uh. Okay. Cool. Ravi, are you here?
Yes.
Okay, cool. So we don't penalize people for missing the classes, but lecture notes, folks, are kind of mandatory, right? It was their duty to kind of summarize what happened in the last lecture. So let's kind of
Oh,
penalize these guys, the guys who were on Tuesday and they did not show up at the start of the class today. Let's penalize them in the lecture notes marks. Just keep a
okay.
note of this. And also the
Okay.
guys who kind of volunteered to do the lecture notes today. They were supposed to be here to do the lecture notes. Awesome. Okay, so at the end of the last class, we were doing um, reduction from anyone. What were we doing in the end of the? Oh, I can't erase this part. Cannot. Anyone? What were we doing at the end of last class? What were we reducing to what? Should I
लाइक एक
just?
अननोन प्रॉब्लम को हमने जो है वो मैप किया था एक नोन प्रॉब्लम को के मतलब काइंड ऑफ रिड्यूस किया था प्रॉब्लम्स को
Okay.
ताकि वो हम उन प्रॉब्लम्स को भी एनपी हार्ड या कंप्लीट कर सकें जो अननोन है।
Okay. Is it Hamza?
यस सर।
Okay, so do you remember the example? What were we listening to what? Which problem?
लाइक हमने एमआईएस और एमवीसी वाली एग्जांपल की थी
Yes. Okay, cool. That
और
is the
साथ
first
एक
example we did. We reduced MIS to MPC. MIS was a known problem. So we're going to just so
सर आपकी आवाज़ बहुत दूर चली गई है।
I think I'm using a different, or this machine is using a different mic than.
अब ठीक है।
Yeah, I'm just trying to figure out. Okay, let me just walk away from the computer. See if you can still hear me. Can you still hear me?
Yes.
Okay, awesome. Cool. So last time what we were doing was last time summary kind of we reduced MIS, the maximum independent set problem, to minimum vertex cover problem. This was kind of a very straightforward, simple example. And then we did a slightly harder problem. Do you remember which one was it? Anyone else other than Hamza?
Color mapping.
Yeah, we did color. But what did we reduce to what? So we had
We used OR gates, I guess, in
थ्री
that.
सेट के साथ कुछ किया था हमने.
3 set to 3 culling problem.
okay, cool. Guys, you have been through the discrete math. 3 set के साथ कुछ किया था हमने is not a appropriate summary of
Sir,
what we did. We reduced the 3 set problem to 3 colorability problem. This is what we did. And the most important part of that thing, if I kind of say it, was to create uh, an OR gate. Simulate basically, हमने simulate किया था. Simulate an OR gate inside a graph. Okay? ये हमने basically किया था. हमने ये कहा था कि if you have a thing like this, you can create a thing like this, and you would end up with whatever x or y you get. This thing would be x or y. All right. Okay, cool. I hope you understood that part. If you did not, please go through it again, because I think this is one of the important reductions. I would also, as an exercise, recommend, so this is still summary of what we are doing. I would recommend trying kind of a third example that we did not do, but what which I think is a straightforward example, is trying to reduce 3 set to 4 colorability. Okay, so 4 colorability is exactly what you think it should be. It's the problem of finding out whether you can color your graph properly with 4 colors. And by coloring it properly, I mean that no two vertices that are neighbors should be colored same. Okay, so one of them is colored square, the other one should be colored triangle. Does this make sense? Shout out from someone.
Yes, sir.
Okay, cool. And you should be able to kind of change this 4 to any k. Okay, where k is at least 3. Actually, this is not a bad idea to uh, think about reducing 3 set to 2 colorability and see how does this work. Can you do it? And what does it mean to color a graph with 2 colors? Okay, just think about it. This is, I think, a nice exercise. All right. The plan for today. Do we have any questions from anyone? Okay, we're gonna see a few more graph problems and maybe some non-graph problems as well. We get time. Let me start with the Hamiltonian path problem. Okay. How do I change colors? Let me use, I don't know, let me start. Okay. This is Hamiltonian path problem. Okay. When I say it's a problem, I should give you a stories graph, such as an example all day today. Um, okay, cool. I should give you a graph as an example. This is a graph. Given a graph, given a graph, this could be directed or undirected. We don't care, right? It's the same. For our discussion today, this is the same thing. It doesn't. directed. G. Decide. Remember, we are talking about the decision problems. Decide whether there exists a path, a simple path. I don't know. This isn't really simple path that that traverses all vertices of G. Okay, so I'm not sure if there is a Hamiltonian path in this graph, but let's see. So in this problem, it's actually important where you start, right? It's not gonna be the same. Let's see. If I start at A, I can go to C, I can go to E, then I can go to D. That would lead me to power. That's not a good idea, right? Okay, let me start at D. So I'm just trying to figure out if there is a Hamiltonian path in this graph. Does everyone understand what a Hamiltonian path is? It's a path of length n minus one. Okay, it's a path that touches every vertex in the graph, and the question is, does there exist one or not? Okay, so I'm just trying to figure out if there is one here. Okay, if I go from D to B, and from B I can only go to A, which is a problem. From A I can go to C. From C I can go to E, and from E I can only go to B. It's a problem. Looks like we don't have a Hamiltonian. Okay.
अगर हम F से शुरू करते हैं तो आई थिंक हम विजिट कर सकते हैं F to D
Okay.
and
Let's
then the
try.
same path.
Let me undo what I did. Okay, so you want to go from F to D?
Yes.
I think it's not gonna work. But let's try. Okay, so F to D to B to A to C to E. Oh, okay, we can. Okay, cool, nice. So there's the Hamiltonian path. You can start in F, you can go to D, you can go to B, you can go to A, you can go to C, and you can go to E. It looks like you can. Cool. So this is a Hamiltonian path problem. You prove the hardness of Hamilton. First of all, does this make sense for everyone? Just raise hands, okay? Raise hands if it makes sense. Okay. There are like 3 hands there. What? No one is. Ask questions, people, if it does not make sense. Okay, I see a few thumbs up. Not enough, not enough. Let me Bilal, does it make sense?
Yes, sir.
Okay, Safla.
Yes, it makes sense.
Okay, Abu Rera.
Yes, sir.
Okay, cool. I guess that's enough. Cool. So this is Hamiltonian path problem, and we prove it NP hard by reducing 3 sat to Hamp. This is not a straightforward reduction. So it's gonna take us a whole class to do this. So I'm gonna skip this one, but I'm gonna do an easier one. Okay, the easier one is gonna be able. Okay, easier is gonna be Ham cycle. So what's a Ham cycle problem? You Hamiltonian cycle problem. Hamiltonian cycle problem is exactly what you expect it to be. It's instead of a path, you're looking for a cycle that touches every vertex. Okay. You know, does there exist a cycle that informally touches every vertex in the graph? Okay. For this graph, it looks like we don't have a Hamiltonian cycle. I'm somewhat sure of that. Because the F does not have an incoming edges. So whatever cycle you choose, you won't be able to come back to F, right? So so what we are going to try now is to do this. We are going to prove that Ham cycle is in NP. Okay. There are two parts to it. Part A is that you need to show that Ham cycle is what? What's the first part of doing this?
It's
This,
NP.
yeah, it's NP. Cool. And the second part is to show that Ham cycle is in NP hard.
NP, huh?
Yes. That's cool. Okay. How do we show that it's NP? This is usually the easier part. Not always, but it's usually the easier part. So how do we show that Ham cycle is NP? Anyone? What's the usual recipe? How do you prove a problem to be an NP? Khadija, verify a yes or no in polynomial. Okay. Well, half of your answer is correct. You only need to, and I'm emphasizing it probably the 10th time, that this entails uh, showing that a polynomial time verification is possible for yes instance. Okay, we don't care about the no instance. The other way to saying this is that there exists a polynomial size certificate. Okay. You guys did a problem like this on the quiz, right? You proved something NP. Which problem was it?
If X is not a prime,
Oh, yes. Okay, so let's actually do that here. So actually, let's do both of these. So on quiz, we had a problem. Let's call it P. given integer x is not a prime. So if this is true and this x is a yes instance, then we need to figure out a way to verify the answer, right? So again, I told you that you think of this as a two-party problem. One is the challenger. This, for example, you're a challenger, and then there's this prover. Okay. Challenger creates an instance. So the instance for this one is x. It throws x at prover, and prover says yes or no. We don't care if the prover says no. Us case mein the story ends here. But if the guy says yes, the challenger, you need to figure out a polynomial size thing. Okay. So let's say that polynomial size thing is whatever. You ask prover, give me a certificate. Okay. Certificate. You get a certificate and you verify it here. Okay. The goal is to figure out what the certificate is. Okay. This certificate needs to be a polynomial time thing. Okay. So if x is if the prover says that x is not an integer, a prime number, then x must be equal to some a times b, okay, where both a and b are integers. So your certificate is basically you ask for an integer that divides x. Okay. Okay, and the guy and the prover returns, for example, a, and you verify whether x over a is an integer. Okay, division is a polynomial time thing. You can do it. Okay, so this kind of proves the whole most important part of the story is to figure out what the certificate is. And the certificate in this case is you ask for an integer that divides x. All right. Does this make sense? Raise hands, folks. Please press the button that says raise hands. You see a raise hand button? Okay. I see just two raised hands. People who are not raising hands. Okay, I see 7 people. Do you have any questions? Okay. Okay, I guess there is enough. I see half of the hands are raised, so I guess it makes sense. So does anyone venture figuring out what would be a certificate for Hamiltonian cycle problem? Poly-size certificate for Ham cycle. Yes. Who do I distract? Bakir is Sam. Do you want to give it a shot? Michelle, you there? Okay, Mohit, what do you think? Okay, awfully quiet. So polynomial size certificate for ham cycle is, I guess I'm just kind of insulting your intellect because it's obvious, right? Polynomial size certificate is just the ham cycle. You just ask them for the list of vertices. So I'm saying list and not cycle because the order matters, right? We are actually asking for the order of vertices in the cycle. If there exists a ham cycle, you just ask them. Um, uh, you just ask them for the order of vertices in the ham cycle, right? And you can just verify that that is actually a cycle. Mohit is asking a question in chat. Let me just read it. So, Professor, can we reduce the ham problem to traveling salesman? Yeah, definitely, definitely. We can actually try it today as well. Okay, so for now, what we are going to do is so this part, saying that the polynomial size certificate exists that we can verify in polynomial time completes this part. ये वाला part हमारा हो गया है, okay? And this is what we need to work on. And for the B part, what we are gonna do is, I think this is interesting, so I'm gonna invite you guys to figure out how to do this. So this is what we are going to do. We are going to prove that we can reduce ham path to a ham cycle. They look very similar problems. So it's kind of intuitive that we should be able to do this. What do you guys think? So let me just copy here's my graph. Oh, graph is here. I can just paste it here, I guess. Okay. So again, यहाँ पे मेरे पास जो problem है ham path में, I have a graph, G, or I would get yes if there exists a ham path. And over here, I want to construct in graph H, and this should have a ham cycle whenever there is a ham path in G. Okay, so the goal is to construct H from G while ensuring that H has a ham cycle if and only if G has a ham path. Okay. So where do we start? Okay, let me think. I think to start, we can make our graph a bit simpler, I guess. Let's construct a graph on, yeah, let's construct the simplest possible graph. Let's construct a graph on just two vertices, okay? So let's say this is my graph. Um, this is my graph. Okay, this is my graph G. All right. This definitely contains a ham path, right? I want to construct a graph from this graph. So I want to construct a graph H that should have a Hamiltonian cycle. Any ideas? How should we do that? But now forget about the direction. Okay, we don't care about the direction. Think of that. I don't know if it helps to think of the direction. But if it helps you think of this as an undirected graph, if that helps. So I'm not sure. Anyone? Any idea? How do we construct a graph from this graph that contains Hamiltonian cycle? So this graph does not contain a Hamiltonian cycle, right?
लाइक
Hamiltonian cycle needs to be a cycle.
सर आइडिया तो ये था ना कि हम उसके एंड को उसके स्टार्ट से ज्वाइन करते हैं, लेकिन हमें ये नहीं पता कि एंड और स्टार्ट क्या है, तो हम आई डोंट थिंक
Absolutely,
सो कि इसको इस तरह से कर सकते हैं.
absolutely, absolutely.
बट सर एक साइकिल में तो स्टार्टिंग एंड एंड एक ही पॉइंट होना चाहिए ना.
Yes, yes. Cycle needs to start and end at the same word. So as a hint, H contains G. H must contain everything that G has. Okay. And what do you think we should do next? How do we make sure that this graph contains cycle? So let me just be slightly more, give you more example. Okay, so let's say this is G1, and here is a graph, let's say G2, which does not contain a Ham cycle. So that's a very okay. So let's say I create a bar like this. Okay. So this graph does not contain. Let's call this graph G2, and I'm gonna create this is H1, whatever H1 is going to be. I'm gonna create another graph H2. In the same way, I'm going to create H1, right? But this graph should not have a Hamiltonian. So whatever operation I'm going to do on G1 to construct H2, I'm going to do the same operation to construct H2 from G2. And this operation should not create a Hem cycle because the original graph does not contain Hamiltonian graph. Does this statement make sense to you guys, what I'm saying? That you need to do exactly same things to G1 and G2 to construct H1 and H2. H1 must contain a Hem cycle and H2 must not. Does this statement make sense? Raise hands, thumbs up, or whatever.
Okay.
Or open your mic and complain about it. So what do we do? Okay, I think people understand what I'm trying to say here. So what do we do? Any stupid ideas? Ahmad? Okay, who else is here? Let's see. Ravid, what do you think? What should we do?
Uh, for the G1, you said they are undirected, right?
You can assume they are
X and
undirected,
U.
yes. Or if they're undirected, then we have a problem. Then G2 also has a path, right?
So how
So
about
for
we
these
introduce
example, assume they are directed.
they are directed? For
Yeah.
G1, we can either introduce another edge or we
Okay.
can like introduce another vertex and connect it with like A and B.
Okay. Okay.
So
And
yeah.
what do we do for H2?
For H2, for G2, I'm not G2 के लिए like Hamiltonian path तो नहीं है G2 में like
नहीं है
हम सारे vertices visit नहीं कर सकते
क्या?
तो इसके लिए
So
इसके
if
लिए
you are
इसके लिए
thinking undirected graph, let me give you another example. If you guys are thinking undirected graphs, okay? So if this were undirected, you could construct something like this: A, B, C, and D. Okay, so this is D, and you can make it like this. This is a graph, and there is no Hamiltonian path here. You cannot. If you, for example, yeah, you cannot visit everything. Right? So let's say this is G3. This is undirected graph. So whatever you construct for G3, H3 should not have Ham cycle. Ravi, do you want to complete your idea?
हम वही करेंगे हम लाइक एक वर्टेक्स लेके उसे सबसे कनेक्ट कर दें और लाइक अगर हम G3 में ऐसा करते हैं
Yeah.
तो आई डोंट थिंक हमारे पास साइकिल आएगा
Okay. Okay. Cool. Awesome. Okay. So here's the idea. Here's what Ravi said we should do. We should create a new vertex. Let's call this vertex, I don't know, Z vertex, and we are going to connect it to everything. Okay. So I'm going to connect this here, and then I'm going to connect this here, and then I'm going to connect this here, this here. And remember, we're going to do exactly the same thing in all graphs, right? Oops. Let's see. I'm gonna, so this is a two-way traffic. Okay. And I'm gonna do the same here for G3. So I'm gonna have C, D, and then C. Currently this is what we have. And now what we're gonna do is we're gonna construct this. Okay. So so over here in H1 we are good, right? Because G1 is yes instance for Hamiltonian path, and H1 is also a yes instance for Hamiltonian cycle. I can go from A to B to Z to A. Okay, so I have a Hamiltonian cycle here. I need to just make this quickly. Okay. G2 is a no instance for undirected graph, and H2 must also be a no instance. Let's see if it is. I can go from A to B, B to Z, Z to C, and C to B, but I cannot go back to A, right? So I can start at B, I can go to Z. So none of these paths give me a cycle. This is a no instance. Let's look at G3. This is also a no instance, and this must also be a no instance for cycle. And if you look carefully, you won't be able to find a cycle here. Okay. Yeah, I'm just trying to convince yourself. Does everyone see? Is everyone convinced, or do you want me to say something? Raise hand if you want me to say something. Oh wow, everyone is convinced. Is it? Is it? Is everyone convinced that this is how it should be? So the convince yourself part is, I think you should do it, but I think the argument is not complete until I say something. Okay. let me just write down the argument. So the argument is, I'm just saying it, even though no one asked for it, but so so the argument is that think of so we need to say two things, okay? One, if G has ham path, then H should have ham side. Okay, this is the first part, and we need to say the other way around as well. If H has a ham cycle, then G must have ham path. Okay, we need to argue about it. This is, we cannot just toy with examples. Examples are there just for our understanding. By the way, the reduction, what's the reduction? We did not write what the reduction was, but let me just write. Reduction is create a new vertex. Vertex, add edges to from, let's call this vertex Z, to from every other vertex in G. Okay, so this is our reduction. And why it works? It works because if G has a Hamiltonian path, let's say there's some arbitrary graph G and this is its Hamiltonian path, right? It must start somewhere, it must end somewhere. I don't know what we can call them, V0 to Vn. What we did was we created a new vertex Z and we connected Z with everything, which means that there must be an edge from, we must have added an edge from Z to V0. We also added it to every other vertex, right? But we also added it to Z. And we must have an edge from V1 to 0, right? And this with the path should create a cycle. Okay, this gives us the first path that we can pick the Hamiltonian path and we can use the edges that we added to create a Hamiltonian cycle. Okay. Now the second part, if H contains, so let's say this is the H that we created, and it contains a cycle. Okay. All right. So within this cycle, since this is a Hamiltonian cycle, it must contain all vertices, which means that it must contain the vertex that we added, Z. Right? Okay. So what happens if we remove Z? Well, if we remove Z, then we get a path from the two vertices which are connected to Z in this cycle. But we only added Z and we did not add anything else, right? We added Z and the edges from N to Z. So if we remove Z and all the edges that we added and created from Z, we must find a ham path. Okay, and this ham path is within G. Does it make sense? But this the point I'm trying to make is that this argument is important. If you don't say this argument out loud, you haven't proved anything. You have just argued about it, gave an example about it, but that's not a proof. Okay, so these two arguments are important for generic G and for generic H. Are we good? Cool. Let me know if there are any questions.
इफ देयर इज अ पाथ और हम ऐड करते हैं एक एजर से कनेक्ट कर देते हैं तो एक साइकिल मिल जाता है, ये तो ठीक है, लेकिन अगर पाथ नहीं था तो हम कैसे प्रूव करेंगे कि ऐड करने से कोई साइकिल नहीं बना?
Cool. Good point. Good point. Does anyone else want to answer this question? So let me just write down Hamza's question. Question, and this is important. I think someone should have asked this question in the last lecture. The question is, we have proved that if G has m path, then H has m cycle. Okay, but how do we know if G does have ham path, then H also does not have ham cycle? Important question. I think very important because someone should have asked this question in the last lecture when we were doing our early reductions. Someone wants to answer this for me? Okay, let me answer it. Okay, let's look at this statement. This statement is saying G is no instance, right? G is a no. Should imply that H is a no. Okay, okay. This is what it is. This is what we want to show. This is the second part of what we want to show. The first part was that G is yes should imply that H is a yes. Well, what is its contrapositive? The contrapositive of this thing is contrapositive of P then Q is, what is it, Hamza? Negation of Q, then negation of P, right?
Yes.
So if I want to prove if P then Q, I can also prove the negation of Q then negation of P, right? And the negation of Q then negation of P is the negation of H is a no, is H is a yes. Then G negation of P, G is yes. Okay. So if we have proved that when H is a yes instance, H contains a Hamiltonian cycle, then G also contains a Hamiltonian path. This is equivalent to saying that when G does not have a Hamiltonian path, then H does not have a Hamiltonian cycle. And we proved it here, right? This was the second part. Okay, does it make sense?
Yes.
Okay, so instead of proving the original statement, which we were supposed to prove, we proved its contrapositive. And we know that a statement and its contrapositive are equivalent. Good, awesome. Okay, what do I want to do next? Let me do what Mohit said in a moment ago. Let's introduce a new problem, which is kind of famous, more famous than ever. Do I want to do something simpler before that? Yeah, sure, why not? So let me do this. You guys remember longest path problem, right? I have kind of made your life miserable by talking with this problem every lecture after the lecture, right? So the longest path problem is that given a graph, again, we don't care about whether the graph is directed or undirected. The problem is equally complex for our context. Given a graph G, but now we have weights, okay? So we have vertices, we have edges, and we have weights on the edges. Find out the longest path, right? But since we are in the CN problem, we should say that given a graph, weighted graph, and a kind of number k, does there exist a simple path? We don't want to visit the same vertex again and again. That has an aggregate. This is how you write aggregate weight of at least k. Okay, so this is the decision version of the longest path problem. I give you a graph and I give you a number k, and I ask you, does there exist a path whose if you sum the weights on its edges, you get something that's more than k, right? Okay, and we want to prove the longest path is NP complete. The first part of that is proving it to be an NP, which is, I think, super simple. The second part is well, also simple. It's not hard after you know traveling salesperson problem. But the second part is proving that longest path LP is in NP hard. Okay, and that would require you to prove a reduction. And the reduction we are going to use is, what do you think we should use? Anyone? Ham path. Ham
I
path.
guess same. No chutney problem.
Yeah, ham path. We can use ham path, right? Okay. Cool. The To me, I think the most important part is just kind of understanding what each step requires. Okay, so at this point, the next step is figuring out what's the input of Hamiltonian path problem and what is required, and what's the input of longest path problem and what's required there. Okay, so Hamiltonian path problem, you're given a graph G, and there is no weight there. Okay, so everything is unweighted. You get vertices and you get edges. The longest path problem, you have to construct a graph G. No, let me call it H, right? Let me call it H. Right. Okay, so you have to construct a graph H. You have to construct V bar, E bar, weight, and you also have to construct K. Okay, this is what LP or longest path instance look like. Again, the demand is same. If this is a yes instance, you should get a yes instance here. If this is a no instance, then you should get a no instance here. Okay, who wants to be a hero? How do we construct a LP instance for a ham path instance? I'm gonna kind of do the same. I'm gonna construct a simple graph G1. I'm gonna construct another graph G2. I'm gonna construct another graph G3. Let me do this. So I'm gonna construct a few yes instances and a few no instances. Okay. I'm using the same graphs जो मैंने पिछले example में use किया था. Okay, so this is a yes instance. This is also yes. This is no, and this is no. Okay, kind of thrown in an undirected graph. All right, so what should I do for H1? What should H1 look like? Anyone?
I guess same.
Okay, so I'm gonna Bilal says should have the same thing. Okay, so I constructed the same graph. Okay, so but now I have to also give weight to the edges, and I also have to specify a k. So what should I
Like Same weights for all the edges, I think. That would
Okay,
result in the same path.
okay, give me a number. Same weight, what do you mean? Like 10?
Like 1,
Okay, let me put 10 here. Okay, what should be K equal to? 10 also, right?
yes.
Okay, okay, this makes it a yes instance, right? There is a there is a path of length 10. Okay, which is fine. This is what was required. All right, let's do the same for H2 and see if we get the same graph as uh, specified. I'm gonna put 10 on both uh, edges, and I'm gonna set K to, what should I set K to? Oh, sorry, the
The
direction.
direction.
Yeah, the
K will be
direction is
20.
K should be equal to 20. Okay, what is K in general? What if there are n
N
vertices
minus
and
1 into W.
okay, cool, awesome. N minus 1. So W is same for all edges, and K is going to be N minus 1 times W. Okay, cool. So this looks good, right? This is also a yes instance, which is what was required. H3, I'm gonna do this. I'm gonna do this. 10 and 10 in K is 20 again. And this is a no instance, right? There is no path of length 20 there. All right, same for this thing. I'm gonna put 10, 10, 10. And our goal now is to find a path length 30, and it's also no instance. So it makes sense, right? So far, I have kind of convinced myself that this is the answer. Now comes the step where you actually prove it, right? You prove that what your claim was is true. Prove two parts, right? Yes implies yes, and no implies no. Okay, sorry. Implies no. Cool. So for the first part, let's say this is A and this is B. For the first part, A, I know that G has a Ham path. Okay, G has the Hamiltonian path. So which means that there exist. So since the graph is same, right? There exists a path of length n minus one, right? So since G contains a simple path which touches every vertex, the length of that path is going to be n minus one. There's no other way to construct a path that touches every vertex, right? So it contains n minus one edges, which means that the sum of weights on all those edges E in the hand path, जो भी path होगा मुझे नहीं पता वो क्या है, is going to be equal to W, जो भी मैंने W रखा था times n minus 1. Okay, so this completes the part of where I say that yes implies yes. Okay, the B, which is no implies no, I'm gonna prove it's contrapositive, right? I'm gonna prove that H is yes implies G is yes. Okay, H comma K. But H comma K is yes means that I have a path जिसका total sum of weights on edges is greater than or equal to K. Okay. But I know, but all weights are same, right? If all weights are same, This implies that EW for all edges is greater than or equal to K over W. All right. But what do we know? We know that we set K is equal to W times N minus 1. Okay. Which means that EW is greater than or equal to, what did I say? The weight on every, what did I
N
do
minus
there?
1.
Oh, N minus 1. Yes. Yeah. Okay. So the weight in here is K over N minus 1. But all weights the same. Sorry, hold on a second. Hold on a second. What I'm trying to do. Let me just be slightly more careful here. So this is the longest path, and it contains the sum of the weights on this path is at least K, and let's just be slightly more careful. Okay. So we know that the sum of weights on edges. So E is the longest path. You catch. The sum of that weight is K. K I know is W times N minus 1. Okay, this is what we fixed. Okay. All right. Second part is that all edges have same weight. ये भी हमने set किया था. This implies, who is humming? This implies that the number of edges in LP is N minus 1. Okay. This implies that LP is actually M path in G. Okay. So there are 2 or 3 steps that you need to be just a little bit careful about. But this completes the second part of the proof. Okay.
So can you explain the two equations?
Which 2 equations? These ones?
The one we fixed. Yes.
Okay. Cool. So we started with this. This is P, this is Q. We assume P to be true. Okay. So P is true means that there is KH is a yes instance, means that H contains, let's write it down, right? So this part was longest path, right? So this means that this part P, this means that H contains a path of length of weight more than or equal to K, because this is a yes instance, right? So this is what I wrote here, that let's let just to be a bit more careful, let P be an edge in LP, the longest path, then the sum of weights is at least K. Okay, this is implied because KH is a yes instance. All right, so great. But we set K to be equal to W times N minus 1. Yes, this is how we constructed H and K. We constructed the edge, which means that the sum of the weights on the edges of longest path is at least W times N minus 1. All right, cool. But we also set the weight on all the edges. All the edges contain weight W. Okay. So if the sum of weights on a bunch of edges is W times N1 minus 1, and each of those weights is W, then there must be exactly n minus 1 edges there, right? So if there are n minus 1 edges in this LP, then this path must actually be a Hamiltonian, because Hamiltonian path is the only path that contains n minus 1 edges. Does it make sense?
Yes, sir.
Okay. Anyone else? Okay. So the next part, which is what uh, Mohit was pointing to, is actually it's not that hard, but let me just traveling में double L होता है या single L होता है यार? How do you pronounce traveling?
डबल एल होता है
Double L, double L. Assuming sales person problem or TSP as it is famously abbreviated. So traveling salesperson problem is that you are given a graph, weighted graph, okay? Or a network, or whatever you want to call it, G. It has weights, it has edges, and it has vertices, edges, and weights. Is there? Oh, I don't care about the weights. I don't really care about the weights. Or do I? Traveling salesperson, maybe. I do care about the weights. I do care about the weights.
Yes, sir.
Okay. Yeah,
Yes.
no, I do care about the weights. Okay. Is there a, and then there is a number K as well. Should I use K? कोई और चीज यूज करते हैं यहाँ पे M यूज कर लेते हैं. Okay. Is there a way to start a tour at some vertex X, visit every other vertex in the graph, and return vertex. So that sum of the weights of edges visited in sequence is less than n. Okay, so maybe I just want to paste the graph. This graph does not contain weights, but maybe I can put some weights there. Okay, so give me numbers. Who's gonna give me numbers today? 2, 5, 3, 9, 1. This is 9, 7. 5 again. Did I use 4 somewhere? 4, 4, 10. Run out of memory. 6, I guess. All right. So here's the thing. This looks very much like what does it look like? Well, in some sense, it looks like longest path. In some sense, it looks like uh, Hamiltonian
Sorry.
cycle problem. But remember, you can, for example, let me just kind of make a distinction here. You are allowed to visit vertices and edges multiple times. Okay. So for example, if I give you a simpler graph, which is just A to B to, I want to create a directed graph. Or a directed graph. Yeah, for this thing, I think I want to create an undirected graph. So do you guys remember this example that we created a while ago? A to B to C to D. Yeah. So this graph does not contain Ham cycle, but uh, it contains a TSP tour of weight. What? What do you think?
5, maybe.
I don't see 5. I see 6. I see
Yes,
6.
6 it is.
Okay, cool. So all you have to do is it's red pen. Why is it selecting red? Okay. So all you have to do is go start wherever you want to start. It doesn't really. What does it? No, it doesn't really matter. Okay, so you can start at A, spend 1 coin, go to D, spend another coin, come back to B, spend another coin, go to C, spend a coin, spend another coin, go back. Okay, it's kind of visited every edge twice, which means that you're gonna spend 6 coins. Okay, so it's there's a tour of with 6 there. So that's the problem that I give you a network, and then think of this as someone who's kind of a salesperson, right? He has limited fuel, and he has to visit um, every kind of part of the city and sell things. So can he do that? And he's allowed to kind of visit uh, multiple parts. If he has to, uh, uh, so he's allowed to visit the same place multiple times if he has to. And we're gonna prove that this is an NPR problem by a reduction, as Mohit said, from Hamiltonian cycle problem. So we're gonna reduce Ham cycle. My writing is deteriorating. Let me just quickly do this in 5 minutes. And Ham cycle to TSP. Okay. Now remember what the problem is in both cases. In Ham cycle, you're given a graph, just a graph. In TSP, you're given a graph. Call this graph H as per our norm. But this graph has vertices, edges, and weights, and a number M. Okay. G only has vertices and edges. Income V dash or E dash. Again, we are trying to find this cycle that starts at a vertex and ends at a vertex, but you're not allowed to visit the same vertex again. And in Ham, in traveling salesperson, you're allowed to do everything. I'm gonna do simple examples. So here is what's the simplest example? I guess this is the simplest example. Let's only work with the undirected graphs this time. All right. No example. Yes, examples. Okay. Make it slightly more elaborate. Okay, cool. So I don't know, G1, G2, G3, G4, G5. Yes, yes, no, yes, and no. Okay. Cool. Ideas. What do we do? How do we construct H? Mohit, Wasif. Okay. This is kind of, I think there are multiple ways to go about doing this, and I encourage you to go about finding other ways, but I'm going to give you one simple way to do this. I'm going to construct H as, I'm going to keep all the vertices. I'm going to do something with edges in a moment, and then I'm going to put weight somewhere here. I'm going to put M here. M is going to be N. W is going to be something. H is going to be something. Okay, let's see what H is. So E is everything. Okay, so I'm gonna construct. So for G1, E is gonna be exactly what it is. For G2, H2 is going to be, I'm gonna add all the missing edges. Okay? Let me use a different color for the missing edges that I'm adding. For let me do it here. Okay, so for G3, I'm gonna add this edge. For G4, I'm gonna add this edge and this edge. For G5, I'm gonna add this edge, this edge, this edge. Did I miss any edge? I guess that's it. Okay, so for weights now, for weights, I'm gonna do this trick. If the edge was originally in the G1, I'm gonna put WE to be equal to 1. Otherwise, I'm gonna put WE equals 2. Okay, so what's gonna happen is that so for example, all these edges are in the original graph, so I'm gonna put 1, 1, 1 here. Or यहाँ पे I'm gonna put 1, 1, 1, 1, and 2 for the edges which were not part of the graph. Similarly, 2, 1, 1, 1, 1, 1, 1, 1, 2, 2, and 2. Oh no, I messed up. No, messed up. This is 2, this is 2 is fine. This is not supposed to be 2. This was an original action. This is 1. This is 1. Okay, similarly, 1, 1, 1, 1, 1, 1, 2, and 2. All right, so I'm looking for a traveling salesperson problem, solution for traveling salesperson problem in this new graph. Now, if there is a way to go start at a vertex, visit all the vertices, and come back, then the number of edges that I'm gonna visit be at least n, है ना? उससे ज़्यादा ही होंगे क्योंकि there is a possibility that I might visit some vertices multiple times, which make me use some edges multiple times. But I'm gonna visit at least each vertex once, which means there are, in this dual, there are at least n vertices. And there is a cycle on these n vertices, which means there are at least n minus 1, sorry, n edges there. Okay, if there are n edges there, then the cost or the cost of that word, yes, the cost of the doer is at least it cannot be less than that, right? Um, and the argument is that it will be equal to n whenever I can find a Hamiltonian cycle. If there is Hamiltonian cycle, I can start at a vertex, visit everything, come back to this vertex without visiting every vertex more than once. And that gives me a tour of size n. If there is no Ham cycle, then I'm definitely going to have to visit a vertex twice, either that, or I'm gonna use an edge that was not initially part of the graph. So if I'm gonna visit a vertex, an edge that was not initially part of the graph, then I'm gonna pay a 2 coin cost for that, which means कि मेरे लिए ये possible नहीं रहेगा. Okay, so that's kind of um, the argument behind it. If there is a Hamiltonian cycle, I can use that cycle to do a tour of size n. And if there is no Hamiltonian cycle, then there is no way to do a tour uh, of within the budget, where my budget is in. Okay. That's about it. So this was somewhat uh, similar to what we did before, in the sense that we constructed weights, which made our problem similar to what we were reducing it from. Does it make sense? Raise hands. One last time, folks. One last request. Raise hands or thumbs up or whatever. Okay, cool. Okay, I see a few raised hands. I'm seeing few questions in the chat as well, which I haven't seen. Okay, Mohit says the proof is a valid approach to this problem. Let S1 be the instance of Ham cycle, Ham path problem. Construct a graph G prime adding weight 1 to all edges instance. And a path will exist from V1 to Vn such that total cost is less than equal to n, visiting all nodes exactly once. I think you should start with the ham path की बजाय ham cycle से start कर लो, right? क्योंकि अगर ham path exist करता है और ham cycle exist नहीं करता, then we will have a problem. Other than that, your idea is pretty much what I am trying to say. So जो TSP problem है ना, this is इसके काफी variant है. So अभी जो मैंने variant आपको बताया, इसमें मैंने आपको कहा कि you can visit edges multiple times. कुछ जगहों पे वो restriction ये होती है कि you cannot use edges multiple times. कुछ cases में so इसका एक और variant है which says कि the vertices of your graph are points on two-dimensional plane. So literally वो cities को लेते हैं और उनके बीच में जो road का distance है उसको edge weights लेते हैं. All of these variants are NP complete. You can prove that. But yeah, okay. I hope this makes sense. All right, guys. I think that's about it for today. Go do practice. जो next Tuesday को हम मिलते हैं, hopefully physically. We'll do quiz and a worksheet. Okay. So practice this. And so maybe हम कोई थोड़ी सी एक extra credit activity भी कर लेंगे Tuesday को. Okay. Hopefully we will meet physically. Otherwise possible नहीं है इसको करना.
सर
क्या?
इज इट पॉसिबल क्या आप जो क्वेश्चन बैंक आपने फाइनल के लिए देना था वो आप इस वीकेंड तक दे दें?
Okay, I'm gonna start working on it. I haven't worked on it. I have to just go and look at past exams and problems and somehow gather them in one place. ठीक है, मैं promise नहीं करता, but I'm gonna work on it. Sure.
ओके सर, ओके.
Sure. Anything else, guys? Okay. Thank you. See you.